And this is the orientation of your satellite or spacecraft in space. We have studied space. How do your spacecraft, which position do you have your spacecraft or your satellite? You need to be able to have measurement. And the interesting part of it is you need to make your measurements with reference to or relative to another object, to another thing. Because you're in the space, how do you know where you are, what position you are, how far you need to go, and all of that? Uh, you need the altitude, actually. And there are two ways to determine altitude. One is using the static attitude determination, the other is dynamic attitude determination. I'm not going to be going into the dynamic attitude determination. You've got a lot of mathematics to do in that. You're going to be using a lot of Euler's equation, Euler's formula, and all of that. However, we're going to be focusing more on the static attitude determination in our class. And the other part, which I said I'm not going to delve into today, is attitude control. This has to do with the mechanisms which you use to adjust and maintain whatever orientation you are, or your spacecraft is, or your satellite is. All right, so that's the part of control. Um, Rish, my apologies for that wrong spelling. Static attitude determination. The difference is simply between static and dynamic. The difference is in the time which you're taking your measurements. For static attitude determination, you do all your measurements at the same time. For instance, you want to know where the sun is at a particular time. You want to know what's the magnetic field, maybe of the Earth. You want to know what's the origin, or that you call that the Earth's origin. You want to know where some particular stars and all of that. You want to take measurements, okay? And basically, what we want to obtain in this case is an estimate, which we call a 3 by 3 BN. Okay, B would refer to the body, N will refer to inertia. You know what's for instance, inertia principle, body at rest. Okay, that's what I mean. INERTIA. So those are the two representatives now. B is the body, N is inertia. And in the study, further in the study, we're going to talk more about that. How do we take measurements? We use sensors. There are actually different type of sensors which we use, and they have different level of accuracies. All right, and the end frame, which is the inertial frame, might be the Earth-centered inertial frame, and we represent it with different vectors. So basically, we'll be studying more of vectors, or we'll be representing our measurements in the form of vector. And then we want to calculate. This is what let me I'm gonna try to make it as simple as possible. So Nita will not run away. So um here is what we don't know. Okay, we assume we know this, we assume we have this, but we don't know this BN matrix, or we call it the direction cosine matrix, or we can call it the rotation matrix. It relates the B frame to some inertia N frame. So that's actually what we'll be doing in today's class. We want to see how to obtain this matrix BN. And like I mentioned, dynamic attitude determination, in this case, all your measurements are taken over time, over a time period. So the best way you can visualize it is actually when you talk about discrete and you talk about continuous. The other one is at a time stamp, at a time, particular time. The other dynamic is over a time period. So dynamic can be looked at as continuous. Um, Static can be looked at as discrete. I think you guys all understand what dynamic and discrete means. All right. So dynamic, it's a much harder problem, obviously, when you're measuring something over time. And that's because it's measured over time. And then you need to also consider some gyro, that's rotation rate measurement. So you don't only consider the time factor, you also consider the rotation rate measurements. Both the sensor data and gyro measurements need to be optimally blended together. That is, you want to try to reduce the error as much as possible. Of course, you also want to try to limit the error in the case of static altitude determination. But problem is not as complex as that of dynamic. In the case of dynamic, you want to use things like Kalman filter to blend this or to perform this optimization. All right. But we're not going to go into dynamic altitude determination. Um, there are different types of or different altitude measurement principles. You can use direction cosine matrix, that is your BN matrix, all right? Can I still write? That is your BN matrix. Okay, which is usually what is unknown. That is what we don't know. So this is a way of measuring altitude. This is a principle we use, one of the principles. There's another principle which we call the Euler angles and quaternion principle. Euler angles provide a way to describe your rotations using three angles. Use your pitch, roll, and yaw. I'm not sure if any one of you have come across this in maybe the textbooks I shared or some materials I sent to you, or maybe during your personal studies. You see, Euler angle is actually one of the most prominently used principle for attitude determination. Then the quaternions are a compact mathematical representation for orientation. This has got to do with a lot of mathematics. Then the gyroscopes and inertial measurement units. The gyroscopes will always measure your angular velocity, and that's what you consider when you're doing your dynamic altitude measurement, and it provides information about the rate of rotation. All right. The only thing that I would point out now between the dynamic and the static is that your dynamic is actually it's more complex, it's more difficult, but it's more accurate. That's the benefit of it. Um, so yeah, now we want to do a bit. We want to go in depth into what we mean by the static attitude determination. And I want to use this example. Take, for instance, you are in a car, and I want to draw that car. Let's create a picture of our car. Say you're in a car. Um, Suppose that is it, and you need orientation is in 3D. I mean in 2D. 2D is two-dimensional. You want to find out what your orientation is. Okay? You don't know where you are at this point. Then this is the school of thought, or there's a question to you guys. How many direction measurements do you need for the 2D? If you have, create a picture. you're in a car, you want to know what your orientation is. You know what I mean by orientation? What's your position? Are you facing the north direction? At what angle? Are you facing the west or the east or the south? At what angle are you doing that? Do you all agree that you need one direction measurement for these 2D case?
Yes.
Okay, tell me, let's talk about it, Ibrahim.
Okay. Um, so you can just, so you're asking that how many measurements do we need for 2D measurement?
Yeah,
And you're using the car as an example where you want to determine in which direction the car is traveling.
yeah.
So but wouldn't if you want to determine the direction of the car, isn't that then a one-dimensional measurement or 1D measurement because you're only looking for the direction?
You have actually you have answered the question, because what it means is this is you have this. This is a 2D environment, right?
Yes.
If you want, simply what you need is you need to just obtain the resultant force, right?
Mm-hmm.
Which will tell you which is sufficient for this to obtain which position or which orientation you have in the studio environment. You
Okay.
all agree with this. Say this is V1 and this is V2. This is what we mean by the two-dimensional space, right?
Yeah.
Then the moment you have it in this way, say you have Y, X, and Z. How many dimension is this now?
That's three-dimensional.
This is three-dimensional. So what we're saying is we are not yet looking at a three-dimensional. We're looking at the case of the two-dimensional. Let me clean up some of this. So I want to look at just X and Y. I'll clean up and redraw this. So I'm only looking at this Y and X. This is how many dimensions?
That's two.
Correct. So here is where you have your car in this two-dimensional space, and you want to determine the orientation of your car, right? How do you determine that? You have the X and Y directions.
You find the resultant for the x and the y.
Thank you. That's it. I can draw it this way, right? And call it the resultant. I can draw it this way and call it the resultant, right? So that is what I mean by you only need one measure. You only need the resultant. You only need the unit direction vector. which is your resultant, which will provide all the required information for your car's orientation. All right. So that's how easy it is when you want to do this in the two-dimensional space. And you can simply use your compass to determine in which direction you're heading, and that's it in 2 dimension. But when it comes to 3D, it becomes more complex. It's not this obvious. All right. And we're going to go into that as well and see. Now we're in the 3-dimensional space, which is different from our 2D. We want to determine, we want to take measurements in this case. The question is also how many measurements are required. Can someone tell me? For the 2D, we know it's 1. For 3D, it's how many?
You need at least 2 measurements
So
for
yeah,
any system.
okay. I thought someone is going to say we need 2. We cannot actually know if we need 2, exactly 2. But we can be sure we need at least 2 measurements for a 3-dimensional space. All right. And that's because you need to consider your rotation, which cannot be sensed with only 1D, with only your resultant force. You cannot sense rotation. The 2 vectors now, or the 2 measurements which you require, there's an important property which you need to take note of. They must not be collinear. Can someone tell me what being collinear means? I need someone to tell me what's the meaning of this. They must not be collinear.
Not moving in the same direction.
Yeah, and that is correct. So from this diagram which I sketched, if you look at okay, suppose we have the sun, right? And we need to take measurements, and this is our space. Let's say this is our spacecraft, and we have put a sensor on our spacecraft to measure the direction of the sun, to take measurements from the sun. Suppose this is pointing now to the sun, and we're measuring that SB, that's the sun, with respect to this body. And then we also have another equipment, another sensor to measure another direction, or to take another measurement in another direction. Suppose that is taking the magnetic field, which is this M, and we have put on this a sensor to measure the magnetic field. Okay. In that case, these 2 vectors M and SB, I can call this MB, all right, because it's with respect to this body. These 2 vectors, what we mean by not being collinear is they must not go in the same direction. They must not point in the same direction. They must point in different directions. Usually, we want it to be perpendicular to each other. You see that in the course of the study. That's what we have here. Other concepts that we need to understand is it is assumed that the inertial direction to a certain object, like you are considering with respect to the sun, your earth, magnetic field direction, stars, moon, and all of that, you assume you already know that inertial direction. You assume that is given before we can determine our attitude. So some parameters that should be given would be your inertial direction. We can call it uh, I. Let's call it I, must be given, or we can call it N, whichever one you prefer, should be given. And now, suppose you have the sun direction, which is usually measured by your sun sensor. I'm going to tell you a bit about the sun sensor, and I expect you guys to have read about this. Suppose you have the sun direction that is measured by this sun sensor, and the direction is that unit vector S. Please note, at S, it's a unit vector, okay? And you also have your magnetic field direction, which is usually measured by a magnetometer, and you're representing that vector as unit vector M. Now, we have got two unit vectors measured by two different sensors, okay, the sun sensor and the magnetometer. And now we want to obtain our Bn. This measurement will usually be done, or the algorithm, let me start using the word algorithm. The algorithm would operate based on two information. One is the information, the measurement from the sensors, and the second will be the given measurement, which has to do with your inertial direction. Okay, so you have the measurement by, let's say, the sun, represented as SB, the one from the magnetometer, represented by NB, and then you have the given, which is usually represented, which has to do with your inertia, and here I've represented it by SN, and that's the sun. N is the inertia, M is the magnetic field, and this is with respect to the inertial direction. Now, there's a big question. How do we find your Bn, the matrix? We call it the rotational matrix. How do you determine that? Can someone tell me? Have you read about how to determine that?
Do not take the inertial
Has read
frame.
about it.
Sorry, do you not take the inertial frame reference and then convert it to the body frame reference and then work it out from there?
Okay, you're on the right path, and I'm gonna show you that. So, okay, this is just a quick one around attitude sensors. You have your sun sensors, like I've mentioned. The sun sensor dictates the position of the sun, and then it's used by virtually all spacecraft to point solar panels towards the sun. You can use it to point your solar panel, you have solar panels on your spacecraft, and then you're using this sensor to point your solar panel towards the sun. Okay, and then you also can use this to point sensitive instruments away from the sun. You don't want that, you don't want the effect of the sun on your instruments or your device in your spacecraft. You want to point them away from the sun if they can be damaged. All right, and there are so many types of these sun sensors, but specifically I want us to think about a photocell. Okay, this is an example of your sun sensors. This photocell usually generates a current that is proportional to the amount of incident sunlight. So it's what you have here. It's S, it's proportional to the amount of incident sunlight, let's say high or N. Okay, and it is in a known orientation on the spacecraft. So that is actually what we call the inertia. It's in a known orientation. You have that value. You know where it is on your spacecraft. Of course, you're fixing it there. It's fixed. And then if you look at this photocell, the diagram, and then you look at the sun, you have rays from the sun directly coming on your photocell, and then you have the normal to the photocell, which is assumed to be your inertia disk. Okay, and then we say that it's proportional. That means okay, sorry, and then it's actually, for me, if you look at this measurement which you're taking from your photocell, you're going to have it make an angle alpha to your normal, or to your point of to your inertial point. So that angle is what we use. We have our current in that angle, at that angle rather, will be equal to your current at inertia at rest, then, or at this normal, then cos alpha. This is a normal, this is just your normal, what do you call it now? Year one trigonometric mathematics. And then you can have your S dot, this is a dot product, your inertial vector or measurement will be equal to cos alpha. Okay, this is the measurement from your sun, from your photocell, and this is the measurement which you already know, the inertia. And then when you take a dot product of it, you can actually obtain this angle between them. All right. And the question is this. I want everyone to, or if you know, you can tell me, is the sun actually the is it good to determine your BN, which is this matrix? Is it going to give you good accuracy? Is it good to use sun for your rotation
I would
matrix? Yes.
I would assume it is, because it's not actually moving in position. It's not basically moving to another point in space or something like that. So I would think then it would be a good idea, because that's the focal point of how planets move around the solar system.
Okay. Any other person? Any other person? Can we reference the sun in determining our cos matrix? Okay. It seems everybody is quiet. Most of you guys are quiet. Yes, it's actually one of the best to use, if not the best, but it's one of the best. Compare it to your electromagnetic field or your magnetic field. The more the altitude, that's the height, would actually affect the accuracy of measurements from your magnetometer. But the sun, because it gives about one, it's fixed, and then you don't expect it to have a lot of variation. It's actually one of those. You can also look at the moon. That's another thing. But yeah, you also look at other, like the stars. But usually when you send a mission to the space, you actually would want to think about using the sun as your reference. There's a table which we're gonna see in the slide. that shows the sensor's accuracy of most of these sensors. Now, why should we use multiple photocells or sun sensor? Can someone help us? Why? Why must we think of using multiple photocells or multiple sun sensor on our spacecraft?
Um, I would think it's because if you have say a payload for imaging, for example, it always points one direction, which is towards Earth, and if it shifts and changes direction, you won't be able to capture any images that the satellite is designed for. So therefore, you need different sun sensors at different points on the satellite to accommodate for that. This is my opinion.
Okay, that's it. Because we need to actually, to be able to determine the actual direction, you need multiple photocells. You need multiple of these to be able to determine the actual direction. So look at it now. That's why I have this cone. This is the normal. This is actually your photocell, and then your point which you know, which is the inertia represented by this unit vector n. By the time this points in one direction, it may be pointing towards the sun, but look at the cone. You don't actually see all of the parts of the cone. So you have another one placed on your spacecraft, but while placing, you need to also put other things into consideration. And that is, you need these photocells to intersect. Okay, you need them to intersect so that or overlap, so that you can actually have proper angles whereby you're measuring your direction from the sun. Okay, and suppose we're using two photocells. In how many places or in how many lines will your photocell intersect?
Sorry, can you repeat the question, please?
Okay, I'm gonna draw that. Suppose we have, I'm drawing a cone because this is the cone which this is actually all we can have see using one, this is our N1, let me call it N1, and this is your photocell 1. Okay, this is your photocell 1, and now you have another photocell. Now let me use another color. I usually like green. Okay. Mm, This is photocell 2, and then you have the normal from there, not the best normal line to draw. Now there's always a cone around your normal line, and this is N2, normal line 2. My question now is, with these two photocells, your cones will intersect in how many lines? you have two cones. You have the red cone and you have the green cone. It's an obvious answer. So I need, well, you may think about it, but it's obvious from this diagram. Can someone tell me?
They will intercept at two places.
Two places in two lines. I wish you could actually show me where they have intersected.
Well, if I look at your drawing, they intersect at two
Yeah.
places.
I should be able to give you permission to show us. Is it possible you write on? Can you write on this slide?
Well, it's intersecting at two different points, I would say there and there, but you can consider that as one point as well.
Okay, that is actually right because it intersects at these 2 points. Now let's go to 3. Suppose you have 3. At how many lines would the cone intersect?
If you had three cones,
Yes.
well, those the two,
Who's speaking?
I'm speaking. So
Okay,
if
go ahead.
I had to draw another cone, then I would imagine it would still intercept. So let's say we have a third cone on this angle, then it would also intercept at two places.
Well, you may not be able to see that from this diagram because you're going to 3, you're going beyond the physical view. By the time you draw that or you simulate it, which I would actually like you guys to try and simulate, just make attempt to simulate it on MATLAB, you would see you're going to have it intersect in one line. Okay, so yeah, it's just something I want you guys to think about and lay your hands on it and see. But basically, you would need, back to our lectures, you would need multiple photocells, which must be in different directions on the spacecraft in order to actually have your sun's actual direction. Okay, that's what is required. So this is the diagram that we drew on that slide. And what happens is when you use these multiple photocells, it creates redundancy all over your spacecraft. And it's very useful. Then it's just like you're running a simulation. And when you're running your simulation, you run for only one iteration. Note that when you have just one iteration, it would, considering you're doing maybe probabilities, that will not be the exact thing, the value, result, or answer which is required. But the only way you can know is when you run over several similar iterations. And the same thing for the sun, you need to set at different directions, different angles, but you must put in consideration that they also need to overlap. You don't just leave them separately. They need to overlap. And Those are just important things to take note of. And here I've emphasized that your sun sensors will provide 0.01 degree accuracy, which is extremely good compared to the other sensors. Okay. This is your magnetometer, and this is used to measure your Earth's magnetic field direction. I've indicated that as MB, unit vector MB. I always emphasize that unit vector, which is used to determine your satellite's orientation relative to Earth's magnetic field. You model based on where we are in our orbit and with respect to the Earth's magnetic field. So you have your inertial point, and then you take measurement from the Earth's magnetic field. All right. This actually, if you go on the PDF, it should play a video where you have the poles rotating, and then you'll be able to see that your north magnetic pole is not actually exactly where we think it is on the compass. You have a variation of about 11.5 degrees between the north magnetic pole and your geographic north pole. So all of that you need to put into consideration when you're also taking your measurements. Here are the pros and cons. For magnetic, that's a magnetometer. It's reliable, it's lightweight, it works well in high temperature. Those are the pros for it. However, it can only be useful when you are taking measurement in LEOs. When you are operating in a low orbit space. If you go above 6,000 kilometer altitude, then it becomes you may not have enough accuracy from it. Okay, and I've indicated the reason here. Because at 200 kilometer altitude, you always will have your 5-degree accuracy. When you go to 5,000 kilometer altitude, you have your 1-degree accuracy. Now compare these to the sun sensor, which gives you 0.01 accuracy. You see how huge difference which you're having here. And then when you go above 6,000 kilometers, you don't have good accuracies anymore. Or you really lose it. It may not work. So these are other sensors which I want you guys to read up on your own. I actually thought we could have some discussions around it, distributing this to each of you. No. Okay. This is what we do. Who's gonna pick this? It's just gonna be a brief discussion like we have had in the past. It's just a task for you to do. Who's gonna take star trackers? I want to read up and discuss that. Who's taking that?
Me.
Ibrahim is taking star tracker. Okay, and who's taking earth sensor?
I'll take it.
Okay, thank you, Nita. And then who's gonna take GPS receivers? I would say I'll say Temba should take this because Temba is not actually taking any.
Yes.
Okay, so
I thought it
there we
was
go.
this.
Okay, so we have Dale to relax for now. All right. So this is the table I was trying to refer to that shows your accuracy ranges. If you look at your magnetometers, you have it between 1 and 5 degree accuracy. If you see your earth sensors, it goes, when you go higher, it's 0.05 degrees. When you're on the low earth orbit, it's 0.1 degrees. Okay. And then you have your sun sensors. It goes 0.01 degrees. That's amazing. Okay. And then your star sensors is 2 arcseconds. And your gyroscopes, which is very good, but it also has its own cons. You need to periodically reset it. Okay. And then your directional antennas. I am so working with SKA project. You should know this. Your accuracy is also 0.01 degrees, and it's typically 1% of the antenna beam width. So yeah, just read up on this, and you have clear understanding of all of this. They're just information you need to be aware of. So here we want to also discuss our altitude determination algorithms. There are two ways of determining your altitude, or two algorithms, not two ways now. There are two algorithms. When we talk about algorithms, what are we referring to? Can someone tell me? When we're talking about algorithm, what do we usually refer to?
A sequence of steps that you computationally use as a code to determine certain situations.
Mathematics. That's my word for it. Nita was you actually trying to be diplomatic with what? But the basic is the mathematical process steps. Okay. And so I have to say that because here we're going to be looking at some mathematics. So there are two basic algorithms. The one is deterministic and the other one is statistical. So I would want us to just focus now in the class on deterministic altitude estimation. You can read up on statistical altitude determination. All right. So if you need much on that, I can also provide it on on statistical altitude determination. So let's look at deterministic altitude estimation. We usually use what we call the triad. Triad, can anyone guess? Triad. Have you heard about triad? Triad, it's simply three. 3, 3, 1, 2, 3. So don't ask me when I'm assuming a vector from 1 to 3. Okay? That's because it's a three-man approach. So we assume 3 vectors, and then we use the 3 vector in building our algorithm. Okay? That's a triad method. And this is how we determine our desired matrix Bn, also known as our rotational matrix or the cosine matrix. Remember the previous slide, I put a big question mark to say, how do we find this matrix? So this is the algorithm. This is the way by which we can obtain this matrix. And it goes in the following steps. Remember, it's an algorithm. It would be nice if any of you can actually write the code that works, or a triad algorithm code. You might find it online and try to run it and see how it works for some examples. So the first thing is you want to introduce a third frame, which is the triad coordinate frame. Remember, okay, just a refresher. Remember you have your body fixed frames, that is this. Then you have your inertial frame, which are your ends. Okay. Now we want to introduce the third frame, or we call it the T frames. All right. And that is the first thing we'll be doing. Your fixed body, those are the measurements you get from your sensors. Okay. Your inertia, those are the measurements which you know. All right. Now you need to introduce something completely, a new frame, which I've represented as T1, T2, T3. All right. Now, the next thing to do is we will have to pick one of our measured vectors. Don't forget, you can measure S from the sun using your don't forget you can measure S from the sun using your sun sensor. You can measure M from the electromagnetic field. You can also measure others, like I said, you should read about. Okay, but in the for illustration, just for illustration's sake, I would want us to use that from the sun and from the magnetic field. All right. So since we said the one from the sun, the measurement from the sun would give us a good or a better accuracy compared to that of the electric field. So I'm assuming here that my T1, remember I have T1, T2, T3 vectors of frames. So I'm assuming that my T1 is equal to my S. All right. And here, I've represented it as B, but I can have it as S1 or SB1. But if you're comfortable with that, SB2 and SB3. Okay. So this will imply T1 will be equal to this, not S2. Okay. I've just written this so you can see a clear picture of it. And I have said it where your S is the known sun direction, it's the measurement from the sun. All right. So that's the first thing you do. Now, the second thing you want to do is you want to construct a second unit vector for the T frame that will be perpendicular to another measurement vector. Okay. I can do a better diagram. I can have a better diagram for each of these. So suppose we have an normal or inertial, we have, oh, why is Dale leaving? This is an important part. I don't want anyone to miss it. And then you have another, I call this my N, this is another N, and here we have another N. Okay, so maybe let's name it N1 and let's say 3 and N2. All right, then you're gonna have you have, suppose, let's use yellow for sun. Suppose you have a measurement, say the sun is here, and you have your measurement from the sun, you call it your S, right? Now you have your body, which is your, what color must I use here? Let me use green. Your fixed body, which also be your B1 to B3. It's B, say B2, B1, and then your B3. All right. So you measure this with respect to your to sun or to something. Now you have the other one for, I use blue. So in which direction will your magnetic field be measured? Now you have the sun here. In which direction will you want to draw that of your magnetic field?
Should be perpendicular to the sun center.
So there's, yeah, so maybe I'm just, okay, that's not, doesn't look perpendicular. Please don't mind my drawing. It's just a sketch. Let's say this is for your hair. Right? This is your sun. All of these are unit vectors. So, and now you want to assume something. Your assumption will be that your S will be equal to your T. All right? That's the first assumption. Then you need to construct a second unit vector. This is where I am. For this, that will be perpendicular to another measured vector. Say your hem. All right? And when we talk of perpendicular, suppose we want to write this MATLAB code. Will it be a dot? Oh, I think I asked this in the last class. So yeah, Nita told me it's going to be a cross product. So that's why we have our S to be perpendicular to your hem, right? And if this is perpendicular to each other, I've answered the question here. Why have I done this? I wanted to ask that why will it be a unit vector as well? Will the result be unit vector for this? If you have this, will your results be a unit vector?
No, you have to. I think you have to divide by the absolute unit vector.
That's not what I'm asking. My question is, if you do this cross product, will you be having a unit vector?
No, according to the notes that you wrote down there.
I like that.
Wouldn't that be the resultant um, of those two unit vectors?
Yeah, but the question is, will you be having a unit vector as well? Okay, I will leave it for you guys to try. You can just go in your MATLAB, write a vector, write another vector, and then multiply do a cross product of them and see if you're going to obtain a unit vector or not. Okay, So basically, that's why we normalize it, and that's why we are normalizing. What I've done here is normalization, so as to obtain T2. So that's the formula for T2. And then we go on to obtain our T3, which is just a cross product of T1 and T2. All right. So now we have been able to obtain our T frames. We have been able to obtain our T1 by assuming our T1 is equal to one of the vectors, which measured vectors. And I would select that with the highest accuracy. All right. Which in this case, I'm selecting that of the sun. The next step is to obtain T2, and obtaining T2 will come as a cross product of measurement from the sun and that of the electromagnetic field, and I normalized it, and I normalized that. My T3 will be obtained by simply doing a cross product of my T1 and my T2. All right. And then I have my T1, my T2, and my T3 values. What do I do with these values? Okay. This is what I was trying to draw. But I've left it as an assignment. I'm not going to mark this now, but something I want you guys to play with. Create an animation and rotate the triad in 3D on MATLAB. Okay? Just play around that. All right? Are we on the same page?
Yeah.
What are you guys thinking? Ibrahim has been quiet. Dale, is Dale back? Is Dale in the class now?
Sorry, I just connected for a moment.
Okay, that's fine. I see everyone is in class. It's okay. You can just mute yourself. It's okay. I want you guys to try this, to create this animation and rotate the triad in 3D on MATLAB. I'm going to ask for this later on. So please just do it at your free time. And then here we go. This tells us it is possible to compute a T-frame direction axis using both our B and N frame. Our B is that the body frame. N frame is your inertial frame component. So what we want to do is we want to create or compute T-frame direction for each of these separately. That is, for the body frame separately, for the inertial frame separately. It's the same formula. Remember, we're using our T1 to be equals to S. That's the generic one. But here for the body frame, we specifically going to be using T1 for the body frame to be equal to this measurement for the body frame. And we're going to do the same for inertia. We're going to do likewise for T2 and T3. Okay? Now, suppose there are no measurement errors. That's important. If there are measurement errors, what do we do? If there are no measurement errors, both sets of triad frame representation will be the same. So wherever you obtain here, it's not highlighting. Whatever value you obtain here will be the same value here. That's what I mean. If there is no error, but definitely you're going to have errors. You're going to have some kind of errors. So you need to estimate the body frame triad with respect to your inertial triad. Inertial frame, and that's we use this to represent. So we're going to create something new completely. And here we'll be having our B estimates because of the error and T. Don't forget, this is the original problem. Let me just remind you. This is the original problem, which we don't know how to find. And that's why we are trying to use the triad algorithm. Now I'm splitting into two parts. One here for B, the other for N. Do you see that? So I'm creating a new matrix for B. So this B becomes this. B with error times T. And then it's N times T. So it's not times. So don't get me wrong. I'm not doing any multiplication. This T is simply your triad, your T frame. All right. So how do we then obtain your B hat T? B what's this representation now? It's not hard. What's this? Underline. It's not underline. What's this? Bar. Yeah, B bar T. So this matrix is actually, if you want to visualize it on MATLAB, it's actually this way. It's a column vector. All right. And the other matrix is also a column vector. So you're going to have your T1. So this might be T1, your B, T1, do we go T2, am I right? These are values, so let's say 0.1, 0.2, and 0. I'm just assuming values here, please guys, don't take me wrong, don't get me wrong. Okay, so this will be your T1B. I'm just assuming these are values which I've obtained for T1B. All right, and then you also have another value for T2B in this form. So that's what I mean by a column vector, which will be another value similar, other values like that. So by the time you put them together, you see you create this bar T matrix. Same thing with your NT. You're going to see it better when we deal with an example. And the final thing is, I want to point your attention to the fact that we are looking for BN. I hope you've not forgotten again. We're looking for BN. We splitted it into two. So we're going to have it as whatever we have in this bar B matrix. Then you're doing a dot product, not a cross product here, by your NT, and then you transpose it. You're transposing this matrix. So you're going to have, let's say it's a 3 by 3 matrix. You're still going to have a 3 by 3 matrix. It's not going to change, but because you are transposing, it becomes a 3 by 3 by 3. This was initially 3 by 3 a 3 by 3. Do you understand this now? So by the time you transpose it, it becomes a 3 by 3 matrix in this form. And that's how you obtain your Bn. And why we have our B having a bar on top is because of that error. So it's an estimate. It's not the true value. It's not the exact value. All right. So remember, this is a static way of attitude determination. If we go further into dynamic attitude determination, you want to actually optimize it to reduce that error as much as possible. All right. Any question? Let me just pause here. Any question? Any
I don't have any
question?
questions.
No.
Okay, thank you, Nita. Okay,
No question.
no question from anyone. Okay, that's fine. Now let's look at an example just to drive home our point. Okay, this is what I'll do. I want us, because we need our MATLAB here. We need to compute this. Okay, this is an example. I'm assuming we have two altitude sensors that were attached to a spacecraft, and we have obtained measurements of vectors S hat and M hat. So let's say the one S, this is for sun, this is for electromagnetic field, and here are the values. This is for electromagnetic field, and here are the values. How do I share this screen and split it? I want to split my screen to run my. Okay, let's do this. Has everybody downloaded this slide?
This slide,
The slide is.
Yes.
yes.
You all have it. Okay, please can you all go to this example on your slide, because I want to go to I want to share my MATLAB code so as to be able to quickly do some computation. Or not the code, my MATLAB command window, just to compute some few things. Then I may be asking you to help me with certain things, so you just call out the values for me. I want to now share my screen. Okay. Can you see my MATLAB page?
Yes.
Okay. And the command window, just the command window.
Yes.
All right, beautiful. So it's easy. So what we want to do is to work out with that with this example. So the example says, suppose two altitude sensors were attached to a spacecraft, and we obtain the following measurements from the sun and from the electromagnetic field. So your SB, let me just clear all of this, CLC, your SB, let's say your SB is 0.8273, right? 0.5 0.0541 and minus 0.0. Is everybody with me?
Yes.
Okay. And now the TR is just a transpose. So this is your vector. The measurement you obtain from the sun, right? Let's do that of the magnetic field. It's 0. Minus 0.8285, 0.5522, minus 0.0955, and then I want to take the transpose of it. That's it. So these are my values for from measurement from the sun, measurement from the electromagnetic field. So the example further says both vectors have no inertial frame components. So these are known values. We have Sn from the sun, minus 0.1517, minus 0.9669, and 0.2050. Transpose, that's the inertial frame component of the sun. The inertial frame component of the electromagnetic field, I call it Mn, is negative 0.8393, 0.4494, minus 0.3044. All right. So we have defined all of these vectors as we have in the example. The question says, using the triad algorithm, construct the components of T1, T2, and T3 in both the body and inertial frames. You can go now to page 24 of the slide. That's where that's the formula we'll be using. So we want to have one for the body frame, the other for the inertial frame. All right. So the first principle is that we're going to make, or the first assumption we're going to make. Now I'm dealing with the body frame. So I want to have T1B, T2B, and T3B. The first assumption to obtain T1B will be what? Someone, please.
The sun sensor direction is the same as T1, I think. The unit vector of the sun.
Unit vector of the
Sensor.
sun. The measurements you obtain from the sun sensor is the same as the measurement for your T1B. So I can simply say my T1B is equals to SB, right? Is it correct to say that?
The assumption, yes, I think so.
Do we all agree with this? Based on the assumption that
Yes.
T1B is equal to SB. Okay, so that is my assumption. And I've obtained my T1B to be that. Then the next step is we have to obtain T2B. We have our SB cross multiplication of that cross multiplied by your electromagnetic field, and then you normalize, right? So my T2B will then be my SB. Someone saying something? Okay, it's fine, but we're almost done. We are actually towards the end of the class. Oh, how do I go back to my? Can we all see this?
Yes.
Yes.
Okay, so let's do our SB cross MB. Let's call that SMB would be cross of your SB and your MB. That is it. Okay. Now that we have obtained as SMB, that's the cross product of the two, we need to normalize it. So let's call this normalize SMB is equal to your norm of SMB, right? Because we have already computed our SB cross MB. So when you normalize this is the value you get. So we want to now obtain our T2B. Your T2B will then become SMB divides by normalized SMB. So this is your T2B value. Okay. So we've got this T2B. Now we need to obtain our T3B. What is our T3B going to be? From our equation, T3B will then be equal to your T1B, cross of your T1B and your T2B, right? This is your T3B. So we have obtained T1B. Oh, Temba, sorry, I could not see your hand was raised. What's your question? Can you go on to ask?
Yeah. Your T2B, you used the
Yes.
divide sign. So why the T3B you use cross instead of the normal times sign?
Okay. Remember that it's a cross product. Okay. We are not doing dot product.
Okay. I don't get it. I thought that T3B you can make it if you wanted to have. I assume that if you wanted to implement it as a dot, then instead you would write a T3B is equal to T1B dot. If you wanted a
No,
dot.
the formula is not a dot product. It's a cross
Yes.
product. They are perpendicular to each other.
So can't you use the normal X times to symbolize that you are
Try.
now using cross?
You can try that, but it's
Okay.
not your normal X. No, you don't have the normal X on MATLAB.
Oh, okay.
You don't have the normal X. You if you want to do X, which is cross, you write it as cross. It's
Okay.
different from say 2 times 3.
Oh, yeah. Okay. I get it now. Thank you.
You see, this is the normal times. This is the normal dot product. But the cross product is not the same thing as this, okay?
Understood. Thank
Okay. So now we have obtained, how many people left?
you. We are all here.
Okay, okay. Because I saw Nita was away, and I hope Dale is still here because he said he will soon be leaving. But I'm almost done with the class. By 6, I should be done. This is just the last thing, the example. And it's needed for us to understand all we have been talking about. Okay, Dale, good to see you here. Now we have obtained T1B, T2B, T3B. Okay, guys. So we now need to remember I said we must compute for body frame and inertial frame. So we need to compute for inertial frame. We do the same thing for inertial frame. We compute we make the same assumption. Let's call this T1n for inertial is our Sn. That's the first assumption, right? And then your T2n, before we compute that, let's do our cross Sn. Let's do Sn. No, Smn. Let's call it Smn is equal to your cross of your Sn and your Mn. All right, that will be your cross. Then you want to normalize it. Normalize Smn would be what? Your norm of N and Mn. So that's, oh, what's that? Oh, sorry. Sorry, that's my error. We are normalizing SMN, the cross product. So that's the normalization. And then, just hold on. If you have a question, let me just finish T2. Okay, T2 and then becomes your SMN divided by your normalized SMN. Okay. Any question? You want to ask a question?
No.
Okay, cool. So it's just the same process. And now I need to obtain my T3n. My T3n would be my T1n, the cross of T1n and your T2n. Okay, and that's our T3n. So we have obtained our T1n, our T2n, and our T3n. All right. So suppose this is your exam and or your a test, and I have asked this similar question to say, using the triad algorithm, construct components of vectors T1, T2, T3 in both the body and inertial frames. Now you see we have been able to obtain for the body what do we call it? T1b, T2b, T3b. So we can let's see all our T's for body. T body and be your T1b, T2b, and your T3b. The matrix. Now you see your T body. Can we all see this?
Yes.
Yes.
So if we go back to the slide on okay, go ahead.
That T-body is the one that has an error with a
Yes,
bar on top.
with
Okay.
the bar on top of your B, or we
Okay.
can call it. Let me just name it well. My B bar B bar BT is what your T body. So just so that's the one you're talking about. This is the one with the bar BT
Okay, thank you.
on slide 24. Okay. So this is your matrix, the 3x3 matrix for your bar BT. Now let's do the NT matrix. NT is what? It will be your T1n and your T2n and your T3n. Now you have this as your NT matrix for the inertia. And this is actually where what I would expect if then you're told to obtain your BN. Remember that you have obtained T1, T2, T3, which is your bar BT for the body, your T1, T2, T3 for your inertial frame. Now, the second part of it, so I would expect you to actually write this out, these two matrices. Okay, that's for question 1. Am I clear?
Yes.
Yes.
Any question? It's like you guys are quiet now. Any question?
You said that's question 1, so that mean it ends on that bar BT together with the NT, or does it mean we have to go all the way down to BN bar?
That's the second part of the question.
Okay, thank you.
Okay. Dale, are you good? Nita, I'm sure you're busy with something because you're quiet.
I'm good for now.
Ibrahim, okay. Okay, Ibrahim,
Good.
Dale is also good. Fine. So we can proceed to the second question. Now, the second question says obtain BN. And you already know from the formula which we have that our Bn is equal to a dot product now of your bar Bt and your NT matrix transpose. All right. So now this is question 2. This is question 2. Obtain Bn matrix. And your Bn matrix is actually your rotational matrix. And it's also the same thing as your cosine matrix. Okay. So we want to obtain our, call it bar B Bn matrix. Remember, it's an estimation, so that's why I have the bar on top, which is equal to, from our formula, the matrix bar BT. Now it's a dot product. Dot, that's your dot, that's how you do your dot product. Then your NT, okay, your NT, and you're transposing. You transpose it. Are we good? And there we go. So this is our bar BN matrix. Okay, guys.
Yep.
Okay. So now that we are happy, we have our rotational matrix, we can then extract anything we want from this matrix. If you recall something that your S, let's say your SB, is it, yeah, let me use which matrix now? I don't have the matrix here on MATLAB here, so I cannot go to the matrix. But if you recall that your SB will be equal to, let me just write it out. Your SB, let's call it SB, will be equal to your matrix Bn Since you guys can see this, so I'm just writing all of it here. Matrix Bn times your Sn. Do you guys recall this slide? And that slide where I said we are only looking for how do we obtain our Bn. Now that we have obtained our Bn, okay, we can deduct our SB, and this is to actually see which of the, you can use this to actually identify which of your measurements vector is more accurate. Okay, remember now we have obtained, I'm not asking that from the question, I'm just explaining further what you can do with your Bn. Suppose you have your Bn and you have your Sn. If you do a multiplication, a dot multiplication of your matrix Bn and your Sn, it gives you the measurement for your sun with respect to the body. So you can actually, but basically in most cases, we would have to calculate and compute our Bn matrix. All right. So, and then we can do whatever we want to do with it. But let's look at something interesting from here. Let's multiply this rotation matrix with our Sn. What's my Sn? Let's just pick one of these. Okay, this is my Sn. I have my Sn here, this one, which is given. Let's multiply, let's say our bar B, Bn matrix, multiply, that's a dot multiplication, by Sn, right? See the value it gives us. What value is this? Can anybody go through this question and check? This should actually be your SB value. Is it?
Yes, it is.
It is your SB value. Okay. Now, that is true because of our formulation. Remember, we are saying we're assuming our T1 to be equal to S1. All right. So now let's look at multiplying on as levelization. Let's look at multiplying with Mn. Remember, we have two measurements given. We have the two measurements, known measurements, the inertial frame components for Sn, and we have for Mn. The one is from the sun, the other one is by the electromagnetic field. So let's use that of the electromagnetic field and see if we're going to obtain MB value. Mn by the bar Bn matrix. Do we have the same value? Compare this result with your MB value.
It's close, but it's not identical.
Yeah, you have a bit of error. You have this differ your MB value which is given is minus 0.8285, and here we have minus 0.8274. You can see the error in that using that accuracy. Using that electromagnetic field. You can see 0.5522 and it differs 0.5525, and the last one is actually accurate. So this tells you that our assumption, or no, this tells you that the sensor measurement from the sun, actually gives more accuracy. But what happens if we had assumed that T2 to be equal to say maybe it's equals to S2 or is equals to M2, or no, say our T2 is equal to MB rather. Maybe this will not be like this. So you can play around, you can make your assumptions, play around it, and if you're sure, since we have that accuracy table, we will be able to go for the one that gives the best accuracy. And of course, we know it's that of the sun. So we are not actually using the magnetic field as our to be equal to our T1 or T2. Rather, we are using the one which we are certain of the accuracy measurement, and that is the sun. I mean, which we're certain it has a higher accuracy measurement, and that is the sun. And that's why our assumption will work in this case. If you're now looking at other sensors, like what I've told some of you to study, and you have values from those sensors, it might actually give close accuracy like that of the sun. If accuracy measure is usually good. And I want you to do some. Oh, hello.
Yes.
Sorry, there's load shedding on my side. That's why I thought everyone is done. But my screen must be blank now. Can you see anything on my?
Can still see it.
Oh, amazing. That's good. Okay. So, I want to give an exercise to you guys. And let me just, is it there on the slide? No, it's not here on the slide. I'm just waiting for power to be back. I need my second screen. Just give me maybe about 2 minutes for power to be on. Okay, perfect. So I'm gonna give an assignment to you guys. Let me stop sharing this code. I'll just go to my whiteboard. All right. So what I want you guys to do is this. Just play with it. You can do a similar thing I've done on MATLAB. You can assume T1, okay, to be equal to M for both the body and inertia. So I want you to do for the body frame, that's body frame, do for the inertia frame, okay, and then here I'm saying assume T1 for body is equal to M. Remember that what we assumed was T1B equals to SB. Okay, assume this and assume this. T1F or N rather equal to your M N. All right, and then do all of the computation and see if this will give more accuracy estimate when you check with regards to M. For M, when we checked using sun measurement, the accuracy is not good. It's not exactly what we had. So I want you to use this assumption and see if the accuracy for hem is the same. Understand that question?
Yes, so basically you just want us to compare if you use the magnetic field as the first sensor, the to then see if the accuracy comes out to be closer to,
Yes.
or if
To be the same, to be exact, not close. Okay. Okay, guys. That is where we're gonna stop today. All right. Our next class will be starting from the satellite attitude control actuators. So just like what some of you have requested, you want me to give an outline before the next class. So here you've got the outlines. This is for control actuators actually. You need to maybe do a bit of reading around reaction wheels, magnetic torques, thrusters, and then your CMGs. And I've put in some relevant literature which may be useful for you. This I'm going to discuss in our next class. Then we go to our the next chapter in our course guide. Okay, we have done the first objective in our course guide. We have done the second objective. We are not done. We still have control. Then we'll finish control and then we start the next objective, the third objective. Any question, please?
yes, the animation with regards to rotating the triad in 3D, can we use these values and just
Yes, use these values.
okay.
Use these values. Okay. Do we take how many minutes now? 10 minutes break. We still need, who's present today?
I am.
It's Ibrahim's day. Yeah, Ibrahim is presenting. Ibrahim, do you have your presentation ready?
Yeah.
You do? Okay, cool. Can we just take 10 minutes break so that when we come back, Ibrahim will make his presentation?
Okay.
Though, if you want to leave, you can leave. But if your internet is good, you can just stay and listen to Ibrahim's presentation. Okay? Ibrahim, can you put up your slide before we leave? So we're gonna return back at 16:25. So yeah.
Okay.
I want Ibrahim. Ibrahim, can you put up your slide?
Trying to figure out how to do that. If I go share content, it just gives me.
You go to share files.